So, there are these things called intermolecular forces that essentially hold everything together. So, as you may know, everything is made out of molecules, which are collections of these tiny little particles called atoms. Here is an image. As you can see, these little dots that I've drawn are like atoms, and they make up this molecule. This is a water molecule. H2O, right? It has two H's and one O, two hydrogens and one oxygen. And it is one molecule. Now, everything is made up of molecules, and they're all attracted to each other somehow. And that's what intermolecular forces are. I'll also call them IMFs. So if you ever see that, that's what they mean. Intermolecular force is IMF. And you can tell the difference between a gas, a liquid, and a solid using intermolecular forces. I'll show you why. So this is a solid, right? You see, I've drawn these molecules here. With the little red circles, I've drawn water molecules. That's what this is. And in anything, all the molecules are always moving. Even in you, even in your skin, even in your ears and your hair, the molecules are always moving. Depending on how fast they move is how much energy they have. So a solid, things are not moving very fast in a solid. The little molecules are sort of stationary. They're bonded together. They're very tight. The intermolecular forces holding them together are very strong. There's low energy and strong intermolecular force, right? This is a picture of a liquid. You can see the molecules are still moving around, but they're spread out farther apart than they were in our solid. And this is why liquid flows, but a solid is hard, right? So that makes sense. So these molecules are moving around, and since they're moving around faster, they have more energy. So since they have more energy, they can break apart the intermolecular forces easier. So they don't have to stay attached as much, which is why liquid is, of course, not solid. And with gases, it shows the same thing. So I accidentally wrote on here low energy, but it's high energy. These gas molecules are moving around super fast, and they have very high energy, right? So they have such high energy, they're moving around so fast that they cannot form any intermolecular bonds. And anything they do, they're weak. So any intermolecular force in a gas is going to be weak. All right? So they hold everything together. And I've made up a little experiment that can show you just how intermolecular forces can be at play in a very cool way. So let me show you. All I've used to do this experiment is a bottle of Fiji water, it has to be Fiji water, in my freezer. So I've taken one of these Fiji water bottles and put it in my freezer for about 2.5 hours. And you would think that it would turn into ice, right? After all, it's been there for 2.5 hours, but it actually hasn't, and I'll show you. You know, that still looks pretty liquid to me. But watch what happens when I hit it. And just like that, it turned into ice. Now remember what I was saying about intermolecular forces before. They are at play here, and I'll explain why. Alright, so what just happened with that experiment? In order to explain it, there's one more thing that I need to show you. So these are water molecules, right? We talked about them earlier. This is our oxygen, and these are our hydrogens. Okay? And this blue line right here, this dotted blue line, are those intermolecular forces, or IMFs, that I talked about earlier. See how they're keeping these molecules bonded together? That's what intermolecular force means. But these are a certain type of intermolecular force called hydrogen bonds. All right? Now, hydrogen bonds are what we would call a dipole-dipole interaction. Now, that I know that's a big word, but all that means is that the top of this molecule has a positive charge on it. It has a slight electric charge, and the bottom one has a negative charge. So they're different from top to bottom. Think of a magnet. You know, a magnet has a positive side and a negative side. And if you put another magnet next together, then one of the magnet's positive sides will attract to the other's negative side. It's the same thing here. The top of this is the positive side, the bottom is the negative side, and it attracts together. The dipoles, the differences attract together. And thus they attach in a dipole-dipole interaction. And since there's a hydrogen here and an oxygen here, it's called a hydrogen bond. And what we did was, of course, lowered the water to a temperature below its normal freezing point. All right, so freezing point, what does that mean? So remember when we looked at these a second ago. So water in its normal form, so just like this, is in a liquid state, right? There's high-ish energy, things are moving around, but there's still bonds that are keeping them together. It's just not a solid. So it's liquid, so it flows, right? There are high-ish intermolecular forces. They're in between solid and gas. High-ish. That's not a scientific phrase, but that's the one that I'm going to use. So they're in that liquid state, and when you take away energy, right? When you take away heat and energy would be interchangeable in that case, then these molecules will stop moving so fast, right? Because where are they putting all the energy they have? They're moving around. So when you take it away, they're going to move a lot slower. And when they move a lot slower, they'll form bonds together, and they'll become a solid like this. And those bonds are hydrogen bonds, right? It's just like what we said. The intermolecular forces will get stronger as you go from a liquid to a solid, right? So why didn't ours freeze? Since water has a certain point at which it's supposed to turn into ice, and we passed that point when I left the Fiji bottle in the freezer for so long, why didn't it freeze? In order for water to go from a liquid to a solid, in order for it to start the crystallization process, that's what we call it. So ice is a crystal. In order for it to start that crystallization process, it has to start from somewhere, right? That seems like an obvious enough thing. And in water like Fiji water, show it again, it's very pure. There's nothing but water in this. If I were to go to my sink in my bathroom and get water from the tap, it's not that pure. There's not just water in it. There's more molecules in there. There's more things in there. That doesn't mean that it's dangerous or toxic for you to drink. That just means there's more things other than water. There's more things in bottled water. There's more things in unfiltered water than there are in just pure water like this. And if I were to freeze tap water, it would freeze no problem, because it would start the crystallization process from one of those things, from one of those other elements other than water. But since there are none of those in our Fiji water, we had to do something else. And if you saw, I shook it, I hit it against the table. That proved as our action that moved the molecules right into the correct place to where they would change from a liquid to a solid. Now, all of our energy was gone, right? So we had already taken away the energy. So we had just as much energy as a solid should have, right? Low energy. But we still had the consistency of liquid. All we had to do is match up the poles correctly. And by hitting it, we did that. So when I say poles, what do I mean? Remember when I said the magnets, right? When we hit the water, the molecules lined up. And when one lines up, one forms a bond, and then another forms a bond, and then another forms a bond, and then another, and then another. And then you saw the ice forms as you go down. Those intermolecular forces caused that to happen. We actually forced them to happen by slamming that bottle against it. Supercooling is a really interesting thing. It's a very neat science experiment. Very easy to do. So I really hope you learned something about it. I really hope you learned something about intermolecular forces, and you can see them every day, right? They hold everything together. They hold you together. They hold what you drink together, what you eat together. They're so integral to us, so integral to understanding chemistry, and incredibly important.